In the spring of 1879, as the industrial age thundered through Europe, and the old certainties of physics seemed unshakable, a child was born in the southern German city of Ulm, who would shatter our understanding of space, time, and reality itself. His name was Albert Einstein, and the world had no idea what was coming. Picture this moment. The same year Einstein drew his first breath, Thomas Edison perfected the incandescent light bulb. Steam engines roared across continents. Scientists believed they had nearly solved all the mysteries of the universe. Newton's laws seemed absolute. Time was constant. Space was fixed. Matter and energy were separate entities that could never touch. The scientific community was so confident in their complete understanding that some professors were advising students to avoid physics because there was nothing left to discover. They could not have been more wrong. That baby in Ulm would grow up to prove that time could slow down, space could bend, matter could become energy, and the universe was far stranger and more beautiful than anyone had ever imagined. But the path to revolutionary genius was anything but straightforward. Einstein's early years were marked by struggle, rebellion, and a mind that refused to accept easy answers. Hermann Einstein gazed down at his newborn son with typical parental hopes. He was a successful businessman, part owner of an electrical engineering company with his brother Jakob. The Einstein family was comfortably middle class, Jewish but not particularly religious, more concerned with practical matters than abstract philosophy. Hermann wanted his son to follow a sensible path, perhaps in business or engineering. He had no way of knowing that this child would one day rewrite the fundamental laws of physics. Einstein's mother, Pauline, came from a wealthy family and brought both financial stability and intellectual curiosity to the household. She was passionate about music and literature, filling their home with piano melodies and stimulating conversation. From the very beginning, the Einstein household valued learning, questioning, and the life of the mind. These early influences would prove crucial in shaping the boy who would grow up to challenge everything. But young Albert was not an easy child. His head seemed unusually large, causing his parents considerable worry. He was slow to speak, so slow that his family feared he might be intellectually impaired. The boy who would later explain the universe in elegant equations struggled to form simple sentences until he was nearly 4 years old. When he finally did speak, he had an unusual habit of repeating everything twice, earning him the family nickname, the Dopey One. The transformation from worried parents to proud family came gradually. Albert's true nature began to reveal itself not through conventional achievements, but through an insatiable curiosity about how things worked. He would spend hours taking apart mechanical toys, not to destroy them, but to understand their inner mechanisms. While other children played games, Albert was fascinated by the invisible forces that made objects move. At age 5, something happened that Einstein would later describe as one of the most important moments of his childhood. His father showed him a simple compass. Albert stared at the needle in wonder, watching it always point north, no matter how he turned the device. Here was invisible force acting across empty space, making the needle move without anything touching it. The young boy was transfixed. This was his first encounter with the mysterious nature of physical forces, and it planted a seed that would eventually bloom into revolutionary theories about the fundamental structure of reality. The Einstein family moved to Munich when Albert was just 1 year old, and it was there that his formal education began. The German school system of the 1880s was rigid, authoritarian, and focused on memorization rather than understanding. Students were expected to sit still, listen quietly, and repeat back exactly what their teachers told them. For a boy who questioned everything and needed to understand the why behind every fact, this was torture. Young Einstein clashed with his teachers from the very beginning. He found their methods stifling and their authority arbitrary. When a teacher explained something, Albert would inevitably ask, "But why?" When told to simply accept and memorize, he would push back. His teachers saw this not as intellectual curiosity, but as disrespect and rebellion. They complained that he was disruptive, argumentative, and unwilling to follow rules. One teacher famously told Einstein that he would never amount to anything. Another suggested that his presence was harmful to the class and that he should leave school entirely. These harsh judgments from authority figures might have crushed another child's spirit, but they only strengthened Einstein's conviction that thinking for yourself was more important than blindly following orders. Despite the conflicts at school, Einstein's intellectual development accelerated rapidly at home. His uncle Jakob introduced him to mathematics, presenting algebra not as a series of rules to memorize, but as a fascinating puzzle to solve. Jakob would tell Albert that algebra was a hunt for a mysterious animal whose name they didn't know, so they called it X. Once they captured this animal, they would know everything about it. This playful approach to mathematics captivated Einstein and showed him that learning could be an adventure rather than a chore. At age 12, Einstein experienced what he would later call his second great childhood revelation. A family friend gave him a geometry textbook, and the boy devoured it with passionate intensity. He spent countless hours working through geometric proofs, discovering the logical beauty of mathematical reasoning. Here was a realm where questions had definitive answers, where truth could be discovered through pure thought, where the relationships between ideas created perfect harmony. Einstein taught himself calculus years before it was taught in school. He would spend entire afternoons working through mathematical problems, lost in a world of numbers and equations. His parents worried that he was becoming too isolated, too focused on abstract ideas. They had no way of understanding that their son was developing the mathematical tools he would later use to revolutionize physics. The young Einstein also discovered philosophy during these formative years. He read Immanuel Kant's Critique of Pure Reason at age 13, grappling with questions about the nature of knowledge, reality, and human understanding. While most teenagers were focused on social activities and practical concerns, Einstein was contemplating the deepest questions about existence itself. His reading extended to popular science books that explained the latest discoveries in physics and astronomy. He learned about the wave theory of light, the principles of thermodynamics, and the mathematical laws that seemed to govern everything from planetary motion to the behavior of gases. Each new discovery raised more questions in his mind. Why did these laws work? What underlying principles connected seemingly different phenomena? Was there some deeper unity hiding beneath the complexity of the natural world? Einstein's relationship with religion evolved during these teenage years. Raised in a secular Jewish household, he initially embraced a passionate but short-lived religious phase around age 12. He followed dietary laws strictly, composed songs in honor of God, and believed deeply in divine providence. But this intense religiosity lasted only about a year before colliding with his growing scientific understanding. Reading popular science books and studying mathematics convinced Einstein that the natural world operated according to logical principles that could be discovered through human reason. This realization created a profound conflict with traditional religious teachings about miracles, divine intervention, and faith-based knowledge. By age 13, Einstein had abandoned conventional religion entirely, replacing it with what he would later call a cosmic religious sense, a deep reverence for the logical beauty and mathematical harmony of the universe itself. This rejection of traditional authority extended beyond religion to encompass political and social institutions as well. Einstein developed a lifelong skepticism toward nationalism, militarism, and blind obedience to authority. He saw these forces as enemies of free thought and individual conscience. These attitudes would later bring him into conflict with the rising tide of German nationalism and eventually force him to flee his homeland. The Einstein family's financial situation began to deteriorate when Albert was 15. Hermann's electrical engineering business struggled to compete with larger companies, and the family was forced to move to Italy in search of better opportunities. They planned to leave Albert behind in Munich to finish his education, but the teenager had other ideas. Einstein found the separation from his family unbearable. But even more importantly, he was facing the prospect of military service in the German army. The thought of donning a uniform and following orders without question was anathema to everything he believed. So at age 15, Einstein made a decision that would change his life forever. He obtained a medical certificate claiming nervous exhaustion, withdrew from school, and renounced his German citizenship to avoid military service. This dramatic action shocked his parents and teachers, but it revealed the strength of Einstein's convictions. He was willing to sacrifice security, conventional success, and social approval to preserve his intellectual freedom. He joined his family in Italy, officially a high school dropout with no clear prospects for the future. But Einstein's apparent academic failure masked a deeper truth. While struggling with authoritarian teachers and rigid curricula, he had been developing the independence of mind that would later enable him to challenge the most fundamental assumptions of physics. His conflicts with authority were not signs of rebelliousness for its own sake, but evidence of a powerful intellect that refused to accept ideas without understanding them thoroughly. The months Einstein spent in Italy were among the happiest of his youth. Free from the constraints of German education and military expectations, he could pursue his interests without interference. He read voraciously, studied mathematics independently, and began to formulate his own ideas about the nature of physical reality. He was particularly fascinated by the relationship between electricity and magnetism, phenomena that seemed mysteriously connected despite their apparent differences. During this period, Einstein wrote his first scientific paper at age 16. The topic was the behavior of light in magnetic fields, and while the paper showed the limitations of his mathematical training, it also demonstrated his remarkable intuition about physical phenomena. He was beginning to think like a physicist, looking for the underlying principles that connected seemingly separate observations. His parents, meanwhile, were becoming increasingly worried about their son's future. A teenager without a diploma or clear career path was a source of constant anxiety. They pressured Albert to pursue practical training that would lead to steady employment. The clash between Einstein's intellectual ambitions and his family's practical concerns would continue for years, creating tension that would shape his character and his determination to succeed on his own terms. As Einstein stood at this crossroads between childhood and adulthood, between conventional expectations and revolutionary thinking, the stage was set for one of the most remarkable intellectual journeys in human history. The boy who had been dismissed by teachers and worried parents was about to embark on a quest that would transform our understanding of reality itself. The question of where Einstein would continue his education became urgent. His parents desperately wanted him to have some sort of formal qualification, some piece of paper that would guarantee his future security. But Einstein had burned his bridges with the German educational system, and his lack of a gymnasium diploma created seemingly insurmountable obstacles. The solution came from an unexpected source. Einstein learned about the Swiss Federal Polytechnic in Zurich, a progressive institution that valued practical knowledge over rigid academic credentials. Unlike German universities that demanded extensive classical education, the Polytechnic focused on science, engineering, and mathematics. Even better, they would accept students who passed their entrance examination, regardless of their educational background. Einstein was 16 when he travelled to Zurich to take the entrance exam. He was 2 years younger than most applicants and lacked the formal preparation they possessed. The examination covered subjects ranging from languages and literature to natural sciences and mathematics. Einstein excelled brilliantly in mathematics and physics, solving problems with an elegance that impressed his examiners. But his performance in languages, literature, and other humanities subjects was mediocre at best. The results were mixed. His mathematical and scientific scores were exceptional, but his overall performance fell short of admission standards. However, the physics professor Heinrich Weber was so impressed by Einstein's abilities that he personally invited the young man to audit his lectures. Weber recognized something special in this unconventional teenager, a spark of genius that transcended formal academic achievements. Despite Weber's encouragement, Einstein needed that diploma to gain full admission to the Polytechnic. His parents enrolled him at the cantonal school in Aarau, a Swiss town known for its progressive educational philosophy. The contrast with his Munich schooling could not have been more dramatic. Swiss education emphasized understanding over memorization, encouraged questioning and debate, and treated students as individuals rather than cogs in an authoritarian machine. Einstein thrived in this environment. His teachers appreciated his curiosity and intellectual independence rather than viewing them as threats to classroom order. For the first time in his academic career, Einstein felt genuinely supported and understood. He formed close friendships with classmates who shared his passion for ideas and his skepticism toward conventional wisdom. The year in Aarau was transformative in ways that extended far beyond academics. Einstein lived with the family of Jost Winteler, a teacher at the school, whose household buzzed with intellectual conversation and political debate. The Wintelers were freethinkers who questioned religious orthodoxy, challenged political authority, and believed passionately in human equality and social justice. Their influence on Einstein's developing worldview was profound and lasting. Einstein fell in love for the first time with Marie Winteler, the daughter of his host family. Marie was intelligent, spirited, and shared Einstein's love of music and literature. Their romance was intense but ultimately brief, as Einstein's focus remained primarily on his intellectual pursuits. The relationship ended when he moved to Zurich, but it taught him something important about himself. His passion for understanding the universe would always compete with more conventional human attachments. At the Polytechnic, Einstein finally found his intellectual home. The curriculum combined rigorous mathematical training with hands-on laboratory work. Students were encouraged to think independently and to question established theories. Einstein studied under some of Europe's leading physicists and mathematicians, absorbing the latest developments in electromagnetic theory, thermodynamics, and mathematical analysis. Yet even in this more supportive environment, Einstein's rebellious nature continued to create conflicts. He had little patience for courses he considered irrelevant and often skipped lectures to pursue his own reading and research. His professors admired his brilliance, but were frustrated by his unwillingness to follow prescribed curricula. Einstein preferred to learn directly from the original papers of great scientists, rather than from textbooks that filtered and simplified their discoveries. Heinrich Weber, who had initially championed Einstein's admission, became increasingly critical of his students' independence. Weber was an accomplished physicist who had made significant contributions to electrical engineering, but he represented an older generation of scientists who valued systematic, methodical research over revolutionary insights. He could not understand Einstein's need to question fundamental assumptions that other physicists accepted without hesitation. The tension between Weber and Einstein reflected a deeper philosophical divide about the nature of scientific progress. Weber believed in careful incremental advances built upon established foundations. Einstein intuited that the most important discoveries would require abandoning cherished beliefs and reconstructing physics from entirely new principles. This difference in approach would eventually lead to an irreparable breach in their relationship. Einstein's closest friend at the Polytechnic was Marcel Grossmann, a brilliant mathematician who shared his passion for theoretical physics. Grossmann was more disciplined in his studies than Einstein, carefully attending lectures and taking detailed notes that he generously shared with his friend. Their friendship was based on mutual respect and complementary strengths. Grossmann provided the mathematical rigor that Einstein sometimes lacked, while Einstein contributed the physical insights that Grossmann admired. Through Grossmann, Einstein was exposed to the most advanced mathematical techniques of his time. He learned about non-Euclidean geometry, tensor calculus, and differential equations that would later prove essential to his revolutionary theories. Grossmann also introduced him to the philosophical implications of mathematical discoveries, helping Einstein understand how abstract mathematical concepts could illuminate the deepest structures of physical reality. Another crucial friendship developed with Michel Bessot, an older student who shared Einstein's love of philosophical discussion. Bessot was widely read in philosophy, literature, and science, and he challenged Einstein to think more deeply about the conceptual foundations of physics. Their conversations often continued late into the night, ranging from the nature of time and space to the relationship between mind and matter. Bessot became Einstein's most trusted intellectual confidant, the person with whom he could explore his most radical ideas without fear of ridicule or misunderstanding. Einstein's romantic life during his Polytechnic years was complicated by his growing relationship with Mileva Maric, the only woman in his physics class. Mileva was from Serbia, older than Einstein, and possessed a formidable intellect that matched his own. She was serious, intense, and completely devoted to physics in a way that few people of either gender were at that time. Their relationship began as an intellectual partnership. Mileva could follow Einstein's reasoning about electromagnetic theory and thermodynamics, offering insights and criticisms that sharpened his thinking. She understood his passion for physics because she shared it completely. Their correspondence reveals two young minds wrestling with the deepest questions about the nature of reality, supporting and challenging each other in equal measure. But their romance also reflected the broader social tensions of their era. Mileva faced discrimination as a woman in a male-dominated field, and her foreign background created additional obstacles. Einstein's parents strongly opposed the relationship, viewing Mileva as unsuitable for their son's future success. They worried that marriage to a foreign woman would damage his career prospects and social standing. Einstein's final year at the Polytechnic was marked by increasing tension with his professors and growing uncertainty about his future. He had excelled in theoretical courses, but struggled with experimental work that required patience and attention to detail. His professors recognized his exceptional abilities, but questioned his commitment to systematic research. Some even wondered whether his brilliance was matched by the discipline necessary for serious scientific work. The decisive moment came during his final examinations. Einstein's performance was solid, but not outstanding. He passed all his requirements and earned his diploma as a secondary school teacher of mathematics and physics. But his grades were not impressive enough to guarantee an academic position. Professor Weber, who had once championed Einstein's admission, now refused to recommend him for graduate study or employment. This rejection was a devastating blow to Einstein's confidence and his plans. He had assumed that his obvious talent would open doors to academic positions, but the reality of academic politics proved far more complicated. His independence and questioning attitude, which he viewed as intellectual virtues, were seen by many professors as signs of arrogance and unreliability. Einstein graduated from the Polytechnic in 1900 at age 21, diploma in hand but future uncertain. He had acquired the mathematical and physical knowledge necessary to understand the cutting edge of scientific research, but he lacked the institutional support that would allow him to pursue that research professionally. He was a brilliant young physicist with nowhere to go, a revolutionary mind trapped in conventional circumstances. The next few years would test Einstein's commitment to his scientific dreams, like nothing before. Without academic support or financial security, he would be forced to find alternative paths to the discoveries that were already beginning to form in his imagination. The boy who had questioned authority since childhood was about to learn whether his intellectual independence was strong enough to survive in a world that demanded conformity and compromise. The years following Einstein's graduation were among the darkest of his life. Here was a young man who had spent his entire education questioning the fundamental nature of reality, who had taught himself advanced mathematics while his classmates struggled with basic concepts, who possessed an intuitive understanding of physics that amazed even his professors. Yet he could not find work. Einstein applied for academic positions across Europe. University after university rejected his applications. Some never bothered to respond. Others sent polite letters explaining that they had no openings for someone of his background. The academic world that had seemed so welcoming during his student years now revealed itself as a closed system, resistant to outsiders who lacked proper connections and recommendations. Professor Weber's refusal to provide references proved catastrophic. In the tight-knit world of European physics, personal recommendations from established professors were essential for career advancement. Without Weber's support, Einstein was effectively blacklisted from academic positions. His brilliance meant nothing if the gatekeepers of science refused to acknowledge it. The financial pressure became overwhelming. Einstein had no family wealth to fall back on, no trust fund to support his intellectual pursuits. His parents, already struggling with their own business failures, could offer little help. He was forced to take whatever work he could find, accepting temporary teaching positions at obscure schools and private tutoring jobs that paid barely enough for basic survival. During this period, Einstein lived in cramped boarding houses, survived on cheap meals, and watched his carefully groomed appearance deteriorate into the disheveled look that would later become his trademark. But the external hardships were nothing compared to the internal doubts that began to plague him. Had his teachers been right? Was he too impractical, too rebellious, too divorced from reality to succeed in the real world? His relationship with Mileva Maric provided both comfort and additional complications. They had continued their romance despite his parents' fierce opposition, and in 1901, Mileva became pregnant with their first child. The pregnancy occurred while Einstein was desperately searching for stable employment, creating a crisis that threatened to destroy both their futures. Einstein's parents were horrified. They had already disapproved of Mileva because of her foreign background and her unconventional career ambitions. Now she represented what they saw as their son's complete abandonment of practical responsibility. Hermann Einstein, watching his own business ventures collapse, could not understand how his son could contemplate marriage and fatherhood without any means of support. The pressure from his family was relentless. They threatened to cut off all contact if Einstein proceeded with his plans to marry Mileva. They painted her as a manipulative foreigner who was ruining their son's chances for success. The emotional toll of choosing between his family and his love interest added another layer of stress to Einstein's already overwhelming circumstances. Mileva returned to Serbia to give birth, and their daughter Liesl was born in early 1902. The exact details of what happened to this child remain one of the great mysteries of Einstein's life. Some historians believe Liesl died in infancy from scarlet fever. Others suggest she was given up for adoption. Einstein never spoke publicly about his first daughter, and all traces of her disappear from historical records after a few brief mentions in private letters. The secrecy surrounding Liesl reflects the social constraints of the era and the precarious position Einstein found himself in. An unmarried father with no steady income could not afford a public scandal. Whatever happened to their daughter, it cast a shadow over Einstein and Mileva's relationship that would never completely lift. Salvation came from an unexpected source. Marcel Grossmann, Einstein's loyal friend from the Polytechnic, had maintained contact throughout these difficult years. Grossmann's father knew Friedrich Haller, the director of the Swiss Patent Office in Bern. Through this connection, Grossmann arranged for Einstein to be considered for a position as a technical expert third class, evaluating patent applications for new inventions. The job was far removed from Einstein's dreams of academic research, but it offered something he desperately needed: steady income and intellectual stimulation. The Patent Office required him to analyze the technical feasibility of proposed inventions, to understand complex mechanical and electrical devices, and to communicate his findings in clear, precise language. These skills would prove invaluable to his later scientific work. Einstein threw himself into his patent office duties with characteristic intensity. He developed a reputation for quickly grasping the essential features of complicated inventions and for writing clear, decisive reports. His colleagues respected his technical judgment and his ability to see through elaborate descriptions to the core principles underlying each device. But the real value of the patent office job lay in what it did not demand of Einstein's time and mental energy. The work was intellectually engaging, but not exhausting. It required focus during office hours, but left his evenings and weekends free for his own research. Unlike academic positions that demanded constant attention to institutional politics and administrative duties, the patent office provided Einstein with the mental space he needed to pursue his deepest scientific interests. The years 1902 to 1905 became Einstein's hidden laboratory, a period when he conducted thought experiments that would revolutionize physics while maintaining the outward appearance of a dutiful civil servant. His small apartment in Bern became the unlikely setting for discoveries that would reshape humanity's understanding of space, time, matter, and energy. Einstein married Mileva in January 1903, a small ceremony attended only by a few friends. His parents had maintained their opposition to the end, but Einstein refused to abandon the woman who had shared his intellectual journey through the Polytechnic years. Their marriage represented both a personal commitment and a declaration of independence from family expectations. The early years of their marriage were marked by both happiness and struggle. Mileva proved to be an invaluable intellectual companion, capable of following Einstein's most abstract reasoning and offering insights that sharpened his thinking. Their apartment buzzed with scientific discussion, mathematical calculations scattered across every available surface. Their first son, Hans Albert, was born in 1904, bringing both joy and additional financial pressure to the young family. Einstein proved to be a devoted father, delighting in his son's development and incorporating childcare duties into his daily routine. The experience of watching a young mind develop reinforced his fascination with the nature of human knowledge and perception. During this period, Einstein formed what he called the Olympia Academy with two close friends, Konrad Habicht and Maurice Solovin. This informal discussion group met regularly to debate philosophical and scientific questions, reading works by philosophers like Spinoza, Hume, and Mach. These discussions helped Einstein clarify his own thinking about the foundations of physics and the relationship between theory and observation. The Olympia Academy sessions were characterized by passionate argument, intellectual honesty, and complete freedom from academic pretension. Here, Einstein could explore his most radical ideas without fear of professional consequences. His friends challenged his reasoning, forced him to defend his assumptions, and helped him develop the clarity of thought that would characterize his greatest discoveries. Einstein's scientific work during these years focused on several interconnected problems that had puzzled physicists for decades. He was particularly interested in the statistical behavior of molecules, the nature of light, and the relationship between matter and energy. These seemingly separate topics would eventually converge in a series of papers that would establish his reputation as one of the most important physicists of his generation. His first major breakthrough came through studying Brownian motion, the random movement of microscopic particles suspended in liquid. This phenomenon had been observed for decades but never satisfactorily explained. Einstein realized that Brownian motion could be understood as evidence for the molecular theory of matter, providing a way to calculate the actual size and motion of individual atoms and molecules. The mathematics required for this analysis was formidable, but Einstein had taught himself the statistical techniques necessary to solve the problem. His paper on Brownian motion provided experimental physicists with specific predictions they could test, offering the first direct evidence for the atomic structure of matter. This work alone would have established his reputation as a significant scientist. But Einstein's mind was racing toward even more fundamental questions. He had become convinced that classical physics contained deep contradictions that could only be resolved through revolutionary changes in our understanding of space and time. The seeds of special relativity were already germinating in his imagination, though he did not yet know where his reasoning would lead. The key insight came through contemplating a thought experiment he had been pondering since his teenage years. What would it be like to ride alongside a beam of light travelling at the speed of light? According to classical physics, the light beam would appear stationary to such an observer, like a frozen wave in space. But Maxwell's equations describing electromagnetic phenomena seem to forbid any such stationary light waves. This contradiction between mechanical and electromagnetic theories troubled Einstein deeply. Both theories had been confirmed by countless experiments, yet they seemed fundamentally incompatible when pushed to their logical extremes. Something had to give, but what? Einstein's genius lay in recognizing that the problem was not with the theories themselves, but with the assumptions about space and time that underlay all of physics. He began to suspect that our intuitive notions of absolute time and absolute space might be illusions, convenient fictions that worked well for everyday experience, but broke down at the extremes of high velocity and electromagnetic phenomena. The breakthrough came in May 1905 during one of Einstein's conversations with his friend Michel Bessot. They had been discussing the relationship between time measurements and the speed of light when Einstein suddenly realized the solution. Time was not absolute and universal, as Newton had assumed. Time could run at different rates for different observers, depending on their relative motion. This insight was so radical, so contrary to common sense and centuries of scientific thinking, that Einstein initially doubted his own reasoning. He spent weeks checking and rechecking his calculations, looking for errors that would restore the comfortable certainties of classical physics. But the mathematics was inexorable. Space and time were not fixed and absolute, but relative and interconnected. The implications were staggering. If time could slow down and space could contract, then matter and energy might be interchangeable. The rigid distinctions that had organized all of physics since Newton began to dissolve into a more fluid and dynamic picture of reality. Einstein wrote up his findings in a paper titled On the Electrodynamics of Moving Bodies, submitted to the German physics journal Annalen der Physik in June 1905. The paper was remarkably free of references to previous work, as if Einstein had derived his conclusions from pure thought rather than building upon the research of others. In many ways, this was exactly what had happened. The paper that introduced special relativity to the world was written by a 26-year-old patent clerk working in isolation from the academic community. Einstein had no access to advanced laboratory equipment, no team of graduate students, no institutional support of any kind. He had armed himself only with thought experiments, mathematical analysis, and an unwavering commitment to logical consistency. the scientific establishment's response to Einstein's paper was initially muted. Most physicists found the ideas too radical to accept immediately. The notion that time could slow down and space could shrink seemed to contradict everything they knew about the physical world. Some dismissed the work as mathematical curiosity with no connection to experimental reality, but a few physicists recognized immediately that they were witnessing something extraordinary. Max Planck, already famous for his work on quantum theory, grasped the significance of Einstein's achievement and began incorporating relativity into his own research and teaching. His endorsement carried enormous weight in the German physics community. Einstein himself was simultaneously exhilarated and exhausted by his breakthrough. He had solved problems that had puzzled him for years, but he also realized that he had opened a door to an entirely new understanding of physical reality. The implications of special relativity would take years to fully explore and understand. As 1905 progressed, Einstein continued his remarkable burst of creativity. In addition to special relativity, he published papers on Brownian motion, the photoelectric effect, and the relationship between mass and energy. Each paper addressed fundamental questions that had stumped the physics community, and each offered solutions that would reshape entire fields of research. The year 1905 would later be called Einstein's miracle year, a period of scientific creativity unmatched in the history of physics. But to Einstein himself, still working his day job at the patent office and caring for his young family, it felt like the natural culmination of years of intense thinking about the deepest questions of physical science. He had no idea that these papers would eventually make him the most famous scientist in the world, a household name synonymous with genius itself. For now he was simply a young father and civil servant who had managed to solve some interesting puzzles about the nature of space, time, and light. The transformation from unknown patent clerk to global icon still lay years in the future, waiting for the world to catch up with the implications of what he had discovered. He had discovered the scientific community's slow recognition of Einstein's achievements reflected a deeper truth about revolutionary ideas. They require time to germinate, to be tested, and to overcome the natural resistance of established thinking. While Einstein continued his daily routine at the patent office, analysing mechanical inventions and electrical devices, his papers began circulating through the small network of theoretical physicists across Europe. Max Planck's endorsement proved crucial in legitimizing Einstein's work. Planck had himself challenged conventional wisdom with his quantum theory, proposing that energy came in discrete packets rather than continuous flows. He recognized in Einstein a kindred spirit, someone willing to follow mathematical logic wherever it led, regardless of how uncomfortable the destination might be. Planck began lecturing about special relativity at the University of Berlin, introducing Einstein's ideas to a new generation of physics students. The experimental confirmation of Einstein's predictions began slowly. His work on Brownian motion provided the first testable results. Jean Perrin, a French physicist, conducted meticulous experiments measuring the random movement of particles suspended in water. His results matched Einstein's theoretical predictions with stunning accuracy, providing the first direct evidence that atoms and molecules were real physical entities rather than useful mathematical fictions. This experimental vindication established Einstein's credibility within the scientific community. Here was not just a clever theorist spinning abstract mathematical webs, but someone whose insights corresponded to measurable physical reality. The success of his Brownian motion work opened minds to his more radical proposals about space and time. Einstein's paper on the photoelectric effect, which would eventually earn him the Nobel Prize, introduced another revolutionary concept. He proposed that light itself came in discrete packets of energy, particles he called photons. This idea seemed to contradict decades of evidence showing that light behaved like a wave, creating interference patterns and exhibiting all the characteristics of wave-like phenomena. The notion that light could be both wave and particle violated fundamental assumptions about the nature of physical reality. Scientists had spent centuries learning to think of waves and particles as mutually exclusive categories. Waves were continuous, distributed phenomena that could overlap and interfere with each other. Particles were discrete, localized objects that occupied specific positions in space. Einstein was suggesting that this basic distinction might be an illusion. The implications extended far beyond optics. If light could exhibit this mysterious wave-particle duality, what about matter itself? Might electrons and atoms also display wave-like properties under certain conditions? These questions would eventually lead to the development of quantum mechanics, a theory even stranger and more counterintuitive than relativity itself. Einstein's most famous equation, E equals mc squared, emerged as a direct consequence of special relativity. In a brief follow-up paper published later in 1905, he demonstrated that mass and energy were interchangeable, two different manifestations of the same underlying physical quantity. A small amount of matter could, in principle, be converted into an enormous amount of energy. This relationship remained purely theoretical for decades. The technology to actually convert matter into energy on a large scale did not exist in 1905, and Einstein himself could not have imagined the practical applications his equation would eventually enable. He was pursuing pure knowledge, trying to understand the fundamental structure of reality without concern for practical applications or technological consequences. Yet even as Einstein celebrated these intellectual breakthroughs, his personal life remained complicated and often difficult. His marriage to Mileva, while intellectually stimulating, was strained by financial pressures and the social isolation that came with their unconventional lifestyle. Mileva had abandoned her own scientific ambitions to support Einstein's career, a sacrifice that created underlying resentment even as she continued to serve as his most trusted intellectual companion. The birth of their second son, Eduard, in 1910 brought additional joy and responsibility to the Einstein household. Eduard would later develop serious mental health problems, but in his early years he was a bright, curious child who inherited his father's love of music and learning. Einstein delighted in teaching his sons mathematics and physics, sharing his wonder at the elegant mathematical relationships that governed natural phenomena. Einstein's growing reputation began to attract attention from established universities. In 1908, he received his first academic appointment as a private docent at the University of Bern, a position that allowed him to give lectures while maintaining his patent office job. His early lectures were sparsely attended, partly because he scheduled them at inconvenient times, and partly because his ideas were still considered too radical for mainstream acceptance. The transition from patent clerk to professor was gradual and sometimes awkward. Einstein had spent years working in isolation, developing his ideas through internal dialogue and informal discussions with friends. The formal academic environment, with its emphasis on hierarchy, protocol, and incremental research, felt foreign and constraining after the intellectual freedom of his patent office years. His first major academic position came in 1909 when he was appointed Professor of Theoretical Physics at the University of Zurich. The salary was modest, barely more than his patent office earnings, but the position represented official recognition of his scientific achievements. Einstein was finally able to pursue physics research as his primary occupation, rather than as an evening hobby. The move to Zurich marked the beginning of Einstein's transformation from outsider to insider within the academic physics community. He began collaborating with other theoretical physicists, attending conferences, and engaging in the formal scientific discourse that shapes how new ideas are developed and accepted. This transition brought benefits but also complications that would affect both his scientific work and his personal relationships. Einstein's teaching style reflected his unconventional approach to learning and discovery. He encouraged students to question fundamental assumptions, to think independently rather than simply memorizing established theories. His lectures were often spontaneous and improvisational, following the natural flow of ideas rather than rigid, predetermined outlines. Students either loved his approach or found it impossibly confusing. The informal atmosphere of Einstein's classes attracted students who were themselves unconventional thinkers. Many would go on to make significant contributions to theoretical physics, carrying forward Einstein's emphasis on conceptual clarity and logical consistency. His influence as a teacher extended far beyond the specific scientific content he conveyed, shaping how an entire generation of physicists approach fundamental questions about the nature of reality. During his Zurich years, Einstein began working on the problem that would consume the next decade of his life and lead to his greatest scientific achievement. Special relativity had resolved contradictions between mechanics and electromagnetism, but it created new problems when applied to gravitational phenomena. Newton's theory of gravity assumed instantaneous action at a distance, but special relativity prohibited any influence from traveling faster than light. Einstein realized that developing a theory of gravity consistent with special relativity would require even more radical changes to our understanding of space and time. Gravity could not be a force in the traditional sense, pulling objects toward each other across empty space. It had to be something more fundamental, something woven into the very fabric of space-time itself. The mathematical tools required for this new theory did not exist in any form Einstein had encountered during his education. He would need to learn entirely new branches of mathematics, geometric concepts that seemed impossibly abstract and divorced from physical intuition. The journey toward general relativity would test not only his scientific creativity, but also his determination to pursue ideas that led into uncharted mathematical territory. Einstein's collaboration with his old friend Marcel Grossmann became crucial during this period. Grossmann had become an expert in differential, geometry, and tensor calculus, mathematical techniques that Einstein suspected might be relevant to his gravitational theory. Their partnership combined Einstein's physical insights with Grossmann's mathematical expertise, creating a collaboration that would prove essential to solving one of the deepest problems in theoretical physics. The work was extraordinarily difficult, requiring years of false starts, mathematical dead ends, and conceptual breakthroughs that had to be carefully tested against experimental observations. Einstein often became so absorbed in his calculations that he forgot to eat, neglected his teaching responsibilities, and lost track of social obligations. His single-minded pursuit of scientific truth took an increasing toll on his relationships with family and colleagues. Mileva found herself increasingly isolated as Einstein's fame grew and his attention turned ever more completely toward his research. She had once been his intellectual equal and closest confidant, but the demands of raising their children and managing household responsibilities left little time for the scientific discussions that had once bound them together. The partnership that had sustained them through their student years and Einstein's early struggles was slowly dissolving under the pressures of success and recognition. Einstein's personality was also changing as he gained confidence in his abilities and recognition from the scientific community. The young man who had once been grateful for any opportunity to discuss physics was becoming more selective about how he spent his time and energy. He began to withdraw from casual social interactions, preferring the company of a few close friends who shared his intellectual interests. This growing isolation was both a strength and a weakness. It allowed Einstein to maintain focus on the most difficult theoretical problems, but it also separated him from the broader currents of scientific and social development. He was becoming a figure apart, revered for his genius, but increasingly distant from ordinary human concerns. The years leading up to World War I were marked by Einstein's growing international reputation and his deepening work on general relativity. He moved from position to position, seeking institutions that would provide the resources and intellectual freedom necessary for his research. Each move brought new opportunities, but also new complications, as he struggled to balance scientific ambition with personal relationships and social responsibilities. By 1913, Einstein had been offered a position at the prestigious Prussian Academy of Sciences in Berlin, the heart of German intellectual life. The offer came with no teaching requirements, a generous salary, and the promise of unlimited time for research. It was everything Einstein had dreamed of during his struggling years, but accepting it would mean returning to the country he had fled as a teenager and entering the very establishment he had once rejected. The decision to move to Berlin would prove to be one of the most consequential of Einstein's life, setting in motion events that would lead to his greatest scientific triumph and his greatest personal crisis. As he stood on the threshold of international fame and recognition, Einstein could not have imagined the challenges and transformations that lay ahead. The move to Berlin in 1914 represented everything Einstein had once rebelled against, yet it offered everything he now needed to complete his revolutionary work. The city pulsed with intellectual energy, home to some of Europe's most distinguished scientists and mathematicians. The Prussian Academy provided not just prestige, but practical resources that smaller universities could never match. Here, Einstein would have access to the latest research, collaboration with brilliant colleagues, and most importantly, the uninterrupted time necessary to wrestle with the mathematical complexities of general relativity. But Berlin was also the capital of an increasingly militaristic German empire, a society organizing itself around concepts of national superiority and military conquest that Einstein found deeply disturbing. The young man, who had renounced his German citizenship to avoid military service, was returning to a country preparing for war on an unprecedented scale. The irony was not lost on him that his search for universal truths about space and time was taking place in a city obsessed with national boundaries and territorial ambitions. Einstein's arrival in Berlin coincided with the final breakdown of his marriage to Mileva. The strains that had been building for years finally became unbearable under the pressure of Einstein's growing fame and emotional distance. Mileva had sacrificed her own scientific career to support Einstein's rise, but she found herself increasingly marginalized as his work consumed more of his attention and energy. The intellectual partnership that had sustained their early relationship had given way to a conventional marriage, where she managed domestic responsibilities while he pursued scientific glory. The couple's fundamental incompatibility became obvious in Berlin's sophisticated social environment. Einstein was invited to dinners and receptions, where Europe's intellectual elite gathered to discuss the latest developments in science and philosophy. Mileva, brilliant though she was, felt uncomfortable in these settings where her foreign background and unconventional education made her an outsider. Einstein, for his part, seemed oblivious to her discomfort, absorbed in conversations about tensor calculus and curved space-time. Their separation was painful, but perhaps inevitable. Mileva returned to Zurich with their 2 sons, leaving Einstein alone in Berlin with his equations and his growing reputation. The divorce would not be finalized for years, but the emotional separation was immediate and complete. Einstein threw himself into his work with even greater intensity, as if mathematical abstractions could fill the void left by the collapse of his personal relationships. the outbreak of World War I in August 1914 transformed Einstein's world in ways he had not anticipated. The international community of scientists that had nurtured his early career suddenly fragmented along national lines. Colleagues who had collaborated freely across borders now found themselves on opposite sides of a conflict that would claim millions of lives. The universality of scientific truth, which Einstein considered one of humanity's greatest achievements, seemed powerless against the tribal loyalties that drove nations to war. Einstein's pacifist convictions put him at odds with the overwhelming majority of his German colleagues. While prominent scientists signed manifestos supporting the war effort and portraying German military action as a defense of civilization itself, Einstein refused to add his name to such declarations. He watched in horror as universities transformed themselves into centers of war propaganda, as professors abandoned objective research to develop new weapons and military technologies. The contrast between Einstein's scientific work and the world around him became almost surreal. While armies slaughtered each other in trenches that stretched across Europe, Einstein pursued equations that described the fundamental structure of reality itself. While nations mobilized their entire populations for total war, he contemplated the mathematical relationships that governed the motion of planets and the bending of light. The disconnect between universal truths and human madness had never been more stark. Yet the war years also proved to be the most productive period of Einstein's scientific career. Free from teaching responsibilities and social obligations, he could devote himself completely to solving the puzzle of gravity that had consumed his thoughts for years. The mathematical challenges were enormous, requiring him to master geometric concepts that even professional mathematicians found difficult. But Einstein possessed something more valuable than mathematical technique. He had an intuitive understanding of physical reality that allowed him to see through mathematical complexity to underlying simplicity. The breakthrough came through what Einstein called his happiest thought. He realized that gravity and acceleration were physically indistinguishable phenomena. Someone falling freely in a gravitational field would experience weightlessness, just as if they were floating in space far from any massive object. This seemingly simple observation contained the key to understanding gravity, not as a force, but as a curvature of space-time itself. Einstein spent months working out the mathematical implications of this insight. The calculations were extraordinarily complex, requiring him to use tensor calculus and differential geometry in ways that pushed these mathematical tools to their limits. He made errors, corrected them, started over, and gradually built up a coherent mathematical framework that described how matter and energy curved the fabric of space-time. The physical picture that emerged from these calculations was breathtaking in its elegance and strangeness. Space and time were not fixed stages on which physical events played out, but dynamic entities that could be stretched, compressed, and curved by the presence of matter and energy. Massive objects like stars and planets created depressions in the space-time fabric, and other objects moved along the straightest possible paths through this curved geometry. What we experience as gravitational attraction was actually objects following geodesics through curved space-time. Einstein's field equations, completed in November 1915, represented the culmination of 8 years of intense theoretical work. These 10 coupled differential equations described how matter and energy determine the curvature of space-time, and how that curvature in turn determined the motion of matter and energy. The mathematics was formidable, but the underlying concept was beautiful in its simplicity. Gravity was geometry. The immediate test of any new theory is whether it can explain phenomena that previous theories could not. Einstein's equations immediately solved a problem that had puzzled astronomers for decades. Mercury's orbit around the Sun showed a slight precession that could not be explained by Newton's gravitational theory. Einstein's calculations showed that this precession was exactly what general relativity predicted, providing strong evidence that his new theory was correct. But Einstein realized that his theory made predictions that went far beyond explaining Mercury's orbit. If gravity was really curved spacetime, then light itself should follow curved paths when passing near massive objects. A beam of light grazing the edge of the sun should be deflected by the sun's gravitational field, bending by an amount that could be calculated from the field equations. This prediction offered a dramatic test of general relativity that could be verified through astronomical observations. The problem was that measuring the deflection of starlight by the sun required observing stars during a total solar eclipse, when the sun's brightness would not overwhelm the faint light from background stars. Such observations were technically challenging and could only be attempted during the rare occasions when total eclipses were visible from accessible locations on Earth's surface. Einstein published his completed theory in a series of papers during late 1915 and early 1916, presenting the scientific community with a radically new understanding of space, time, and gravity. The response was mixed. Some physicists immediately recognized the profound beauty and explanatory power of Einstein's equations. Others found the mathematics too abstract and the physical concepts too far removed from everyday experience to accept readily. The war made international scientific communication difficult, so Einstein's work was initially known primarily within Germany and neutral countries. But even in wartime, scientific ideas could not be completely contained by national boundaries. Copies of Einstein's papers made their way to scientists in Allied countries, where they generated intense interest despite the political tensions that surrounded any intellectual exchange with German scientists. Willem de Sitter, a Dutch astronomer, played a crucial role in communicating Einstein's ideas to the English-speaking scientific community. De Sitter obtained copies of Einstein's papers and wrote detailed explanations for British scientists, including Arthur Eddington, who would later become one of Einstein's most important advocates. Through de Sitter's efforts, plans began to form for testing Einstein's prediction about the deflection of starlight during the next accessible solar eclipse. Einstein himself was confident in his theory's correctness, even before experimental confirmation. The mathematical elegance of the field equations and their ability to explain previously mysterious phenomena convinced him that he had uncovered fundamental truths about the nature of reality. When asked what he would have done if the theory had failed experimental tests, Einstein reportedly replied that he would have been sorry for the dear Lord, because the theory was correct. This confidence reflected more than scientific arrogance. Einstein had developed an almost mystical faith in the power of mathematical reasoning to reveal the deepest structures of physical reality. He believed that the universe was rationally constructed according to mathematical principles that human minds could discover through careful thought and logical analysis. His success with special relativity and now general relativity seemed to confirm this philosophical conviction. The completion of general relativity marked the end of one phase of Einstein's career and the beginning of another. He was no longer an unknown patent clerk pursuing physics as an evening hobby, nor even a struggling young professor trying to establish his reputation. He was now recognized within the scientific community as one of the most important theoretical physicists of his generation, someone who had fundamentally changed our understanding of space, time, and gravity. Yet Einstein's personality remained remarkably unchanged by his growing fame within scientific circles. He continued to dress carelessly, to speak his mind regardless of social conventions, and to pursue his research with the same passionate intensity that had characterized his work since his student years. Success had not made him conventional or cautious. If anything, it had reinforced his conviction that thinking independently was more important than following accepted wisdom. The war years also deepened Einstein's political consciousness in ways that would profoundly influence the rest of his life. Watching the conflict destroy European civilization and claim millions of lives convinced him that nationalism and militarism were among humanity's greatest threats. He began to speak out publicly against war, calling for international cooperation and the establishment of supranational institutions that could prevent future conflicts. These political views put Einstein at odds with many of his German colleagues, who saw his pacifist stance as unpatriotic and potentially treasonous. Some questioned whether someone who refused to support his country during wartime deserved to benefit from German academic institutions and scientific resources. Einstein's response was characteristically direct. He considered himself a citizen of the world first and a German citizen only by accident of residence. The tension between Einstein's scientific work and his political convictions would only intensify in the years following the war. His theories had emerged from pure thought and mathematical analysis, but they would soon be tested against experimental observations that could either confirm or refute his most fundamental insights. The results of those tests would transform Einstein from a respected scientist, known mainly within academic circles, into a global celebrity whose name became synonymous with genius itself. As 1918 approached and the war ground toward its exhausted conclusion, Einstein stood at another crossroads in his remarkable life. Behind him lay years of theoretical breakthrough that had revolutionized physics. Ahead lay the prospect of experimental confirmation that would either validate his insights or force him to reconsider everything he believed about the nature of reality. He could not have imagined that within a few years, newspaper headlines around the world would proclaim his theories confirmed, making him perhaps the most famous scientist who had ever lived. The boy who had questioned authority since childhood, who had been dismissed by teachers and rejected by professors, who had struggled for years to find steady employment, was about to become the embodiment of scientific genius for an entire generation. But with that fame would come pressures and responsibilities that would test his character in ways that pure research never could. The transformation from patent clerk to global icon was about to begin. The year 1919 dawned with Europe exhausted from 4 years of unprecedented destruction. Empires had collapsed, millions had perished, and the old certainties that had governed European civilization lay in ruins. But for Einstein, still working quietly in his Berlin study, 1919 would bring the moment when his revolutionary ideas about space and time would be put to their ultimate test. The opportunity came in the form of a total solar eclipse that would be visible from the South Atlantic on May 29th. Arthur Eddington, the brilliant British astrophysicist who had become fascinated with Einstein's general relativity through Willem de Sitter's communications, saw this eclipse as the perfect chance to test Einstein's most dramatic prediction. If Einstein was correct, starlight passing near the sun's edge would be bent by exactly 1.75 arc-seconds, a deflection twice as large as Newton's theory would predict. Eddington faced enormous practical and political obstacles. Britain and Germany had been mortal enemies for 4 years. Many British scientists viewed any collaboration with German researchers as tantamount to treason. The idea that British expeditions would spend significant resources testing the theories of a German pacifist seemed almost absurd to those who had lived through the war's horrors. But Eddington possessed both scientific vision and remarkable courage. He recognized that Einstein's work transcended national boundaries, representing a fundamental advance in human understanding that belonged to all humanity rather than any single nation. Despite fierce criticism from colleagues and the press, Eddington organized 2 eclipse expeditions to test Einstein's predictions, one to the island of Príncipe off the west coast of Africa, the other to Sobral in Brazil. The technical challenges were formidable. Measuring the positions of stars during an eclipse required extraordinary precision, with equipment that had to function perfectly under difficult field conditions. The slightest vibration, temperature change, or atmospheric disturbance could ruin months of preparation. The total eclipse would last only a few minutes, providing a narrow window during which crucial observations had to be completed. Einstein waited anxiously in Berlin for news of the expedition's results. He had complete confidence in his theory's mathematical foundation, but experimental science had a way of humbling even the most elegant theoretical predictions. The measurements would either vindicate years of intensive work or force him to reconsider everything he believed about the nature of gravity and space-time. The initial reports from both expeditions were ambiguous. Clouds had interfered with observations at Principe, while technical problems had plagued some of the measurements at Sobral. Eddington spent months carefully analysing the photographic plates, comparing the apparent positions of stars during the eclipse with their positions when the sun was elsewhere in the sky. The work required painstaking attention to detail and sophisticated corrections for various sources of experimental error. When Eddington finally announced his results at a joint meeting of the Royal Society and Royal Astronomical Society in London on November 6, 1919, the scientific world held its breath. The measurements showed that starlight was indeed deflected by the sun's gravitational field, and the amount of deflection matched Einstein's predictions with remarkable accuracy. Newton's theory of gravity, which had reigned unchallenged for over 2 centuries, had been overthrown by a German theorist working with nothing but thought experiments and mathematical analysis. The reaction was immediate and electric. J.J. Thomson, the discoverer of the electron and president of the Royal Society, declared that Einstein's work represented perhaps the greatest achievement in the history of human thought. The London Times ran headlines proclaiming that space was curved and time was relative, concepts so foreign to everyday experience that many readers could barely comprehend what they meant. Einstein received news of Eddington's confirmation through a telegram that reached him in Berlin on November 27th. His reaction was characteristically understated. He had been so confident in his theory's correctness that experimental confirmation felt more like vindication than surprise. When asked how he would have reacted if the experiments had contradicted his predictions, Einstein famously replied that he would have felt sorry for the good Lord, because the theory was correct regardless. But while Einstein remained calm, the world around him exploded with excitement and confusion. Newspapers across Europe and America struggled to explain relativity to readers who had never encountered such radical ideas about the nature of reality. Space could curve, time could slow down, matter could become energy, and gravity was not a force but geometry itself. These concepts challenged fundamental assumptions about the world that had remained unquestioned since ancient times. The press coverage transformed Einstein overnight from an obscure theoretical physicist into a global celebrity. His wild hair, rumpled clothing, and absent-minded professor appearance made him an instantly recognizable figure. Photographers followed him through Berlin streets. Reporters besieged him with questions about his theories and their implications. He received hundreds of letters from admirers, cranks, and fellow scientists seeking to understand his work. Einstein found this sudden fame both amusing and burdensome. He had spent years working in relative obscurity, free to pursue his research without external pressure or public scrutiny. Now, every aspect of his life attracted attention. His personal relationships, political views, and casual comments became subjects of international interest. The privacy he had treasured as essential to creative thought was rapidly disappearing. The public fascination with relativity reflected deeper currents in post-war culture. The old certainties that had governed European civilization had been shattered by 4 years of unprecedented destruction. Traditional authorities in politics, religion, and social organization had lost credibility. People were hungry for new ways of understanding reality, and Einstein's theories seemed to offer a glimpse into a universe far stranger and more wonderful than anyone had imagined. Einstein's Jewish background added another layer of complexity to his sudden celebrity. In a Europe where anti-Semitism was rising and nationalist movements were gaining strength, Einstein represented both the cosmopolitan nature of scientific truth and the vulnerability of Jewish intellectuals in an increasingly hostile environment. Some celebrated him as proof of Jewish genius, while others viewed his success with suspicion and resentment. The scientific community struggled to absorb the implications of general relativity, while experimental confirmation had established the theory's validity. Understanding its deeper meaning required mastering mathematical techniques that few physicists possessed. Universities scrambled to offer courses in differential geometry and tensor calculus. Graduate students who had planned careers in experimental physics suddenly found themselves grappling with abstract mathematical concepts that seemed far removed from laboratory work. Einstein began receiving invitations to lecture at universities around the world. His first major international appearance came during a visit to Britain in 1921, where he spoke to packed auditoriums filled with scientists, intellectuals, and curious members of the public. His lectures combined mathematical rigor with philosophical reflection, helping audiences understand not just what relativity said about the universe, but why these insights mattered for human understanding. The British visit was remarkable for both its scientific content and its symbolic significance. Here was a German scientist being welcomed enthusiastically in a country that had recently been at war with Germany. Einstein's presence seemed to demonstrate that scientific truth transcended national boundaries and that intellectual cooperation could bridge even the deepest political divisions. Einstein's growing fame also attracted criticism and controversy. Some physicists questioned whether his theories were really necessary, arguing that classical physics could be modified to account for the observed phenomena without abandoning familiar concepts of absolute space and time. Others attacked relativity on philosophical or even religious grounds, claiming that Einstein was undermining objective truth and moral certainty. The most vicious attacks came from anti-Semitic groups that portrayed relativity as Jewish physics designed to corrupt Aryan science. These critics ignored the mathematical elegance and experimental confirmation of Einstein's work, focusing instead on his ethnic background and political views. Einstein watched with growing alarm as scientific questions became entangled with racial ideology and nationalist propaganda. Despite the controversies, Einstein's reputation continued to grow throughout the early 1920s. He received the Nobel Prize in Physics in 1921, though notably for his work on the photoelectric effect rather than for relativity. The Nobel Committee remained cautious about embracing theories that seemed to challenge fundamental assumptions about the nature of reality. Einstein used his Nobel lecture as an opportunity to explain the conceptual foundations of his work, emphasizing the logical necessity of his conclusions rather than their revolutionary implications. Einstein's personal life during this period was marked by both triumph and turmoil. His divorce from Mileva was finalized in 1919, the same year that Eddington's observations confirmed general relativity. He married his cousin Elsa that same year, a relationship that provided emotional stability but lacked the intellectual partnership he had shared with Mileva during his early career. His relationship with his two sons remained complicated by distance and the bitter circumstances of his divorce. Hans Albert, his older son, would eventually become an accomplished engineer, following a more practical path than his father's theoretical pursuits. Eduard, his younger son, showed early promise but would later develop serious mental health problems that would cause Einstein profound anguish throughout his life. Einstein's fame also brought financial security for the first time since his early struggles. Lecture fees, book royalties, and consulting arrangements provided income that freed him from economic anxiety. He could now focus entirely on research without worrying about practical necessities, though he remained characteristically indifferent to material possessions and social status. The 1920s saw Einstein attempting to extend his geometric approach to gravity to other fundamental forces. He became convinced that electricity and magnetism could also be understood as manifestations of space-time geometry, leading him to search for a unified field theory that would describe all physical phenomena through a single set of equations. This quest would consume much of his remaining scientific career, though it would ultimately prove unsuccessful. Einstein's unified field theory work reflected his deep philosophical conviction that the universe possessed an underlying logical structure that human reason could discover. He believed that apparent complexity in natural phenomena masked deeper simplicities, and that mathematical analysis could reveal the elegant principles governing all physical processes. This faith in rational understanding would sustain him through decades of difficult calculations and disappointing results. The search for unification also reflected Einstein's growing isolation from mainstream physics research. While younger physicists were developing quantum mechanics, the strange theory of atomic and molecular behavior that would revolutionize 20th century science, Einstein remained focused on classical field theories and geometric approaches to fundamental forces. His conviction that quantum mechanics was incomplete would put him at odds with most of his colleagues for the rest of his career. Einstein's political activities also intensified during the 1920s. His pacifist convictions, strengthened by witnessing World War I's devastation, led him to support international cooperation and disarmament efforts. He served on various peace organizations and spoke out against nationalism and militarism. These activities made him a target for right-wing groups that viewed pacifism as unpatriotic and internationalism as a threat to national sovereignty. His growing involvement in Zionist causes added another dimension to his public persona. Though not religious in any conventional sense, Einstein came to believe that Jewish people needed a homeland where they could develop their culture and protect themselves from persecution. His support for Jewish settlement in Palestine brought him into contact with other prominent Jews working for Zionist goals, while also making him a target for Arab nationalists and anti-Zionist Jews who opposed the Zionist project. Einstein's travels during this period took him around the world, from Europe to America to the Far East. Everywhere he went, crowds gathered to hear the man who had revolutionized physics and challenged humanity's understanding of reality itself. His lectures drew audiences that included not only scientists and intellectuals, but ordinary people curious about the strange new universe that Einstein had revealed. These journeys also exposed Einstein to different cultures and political systems, broadening his perspective on human affairs and reinforcing his conviction that scientific truth transcended cultural boundaries. He observed the rise of fascist movements in Europe, the struggles of developing nations, and the growing tensions that would eventually lead to another world war. His experiences as a global celebrity gave him a unique vantage point for understanding the political currents that were reshaping the 20th century world. As the 1920s progressed, Einstein's position in the scientific community became increasingly complex. He remained enormously respected for his past achievements, particularly general relativity, but his current research interests were diverging from the mainstream of physics development. While younger physicists were making rapid progress in quantum mechanics and atomic physics, Einstein continued his lonely quest for a unified field theory that most colleagues considered premature, if not impossible. The tension between Einstein's status as a scientific icon and his growing intellectual isolation would define the next phase of his career. The man who had revolutionized physics through radical thinking was now seen by many as a conservative figure, resistant to new ideas and clinging to outdated philosophical assumptions. Yet Einstein remained convinced that his approach was correct and that time would vindicate his search for deeper unifying principles. The stage was being set for the great intellectual battles of the 1930s, when Einstein's opposition to quantum mechanics would put him in direct conflict with younger physicists who saw quantum theory as the future of science. The debates between Einstein and advocates of quantum mechanics would become legendary, illuminating fundamental questions about the nature of physical reality and the limits of human knowledge. But even as these scientific controversies developed, darker forces were gathering in Germany that would soon threaten Einstein's safety and force him to abandon his homeland once again. The rise of Nazi ideology would transform Einstein from a respected, if controversial, scientist into a refugee seeking safety in a foreign land. The boy who had fled German authoritarianism as a teenager would find himself fleeing German totalitarianism as a world-famous adult, carrying with him the accumulated wisdom of a lifetime spent probing the deepest mysteries of the universe. As Einstein entered the 1930s, the world around him was transforming in ways that would force him to confront the most dangerous political currents of the 20th century. The economic collapse following the 1929 stock market crash had created conditions of desperation and social upheaval across Europe. In Germany, extremist movements were exploiting public fear and resentment, offering simple explanations for complex problems and promising radical solutions to national humiliation and economic hardship. Einstein watched with growing alarm as the Nazi Party gained political strength throughout the early 1930s. Their ideology combined virulent anti-Semitism with pseudo-scientific theories about racial superiority, directly threatening everything Einstein represented as a Jewish intellectual committed to international cooperation and rational discourse. Nazi propaganda increasingly targeted prominent Jewish figures, portraying them as corrupting influences on German culture and obstacles to national renewal. The scientific community in Germany was not immune to these political pressures. Some physicists began embracing concepts of German physics that rejected Einstein's theories as foreign contamination of pure Aryan science. They argued that relativity and quantum mechanics represented Jewish attempts to undermine objective truth and replace solid experimental knowledge with abstract mathematical speculation. These attacks went beyond scientific disagreement to encompass racial hatred and nationalist fanaticism. Einstein's position at the Prussian Academy became increasingly precarious as Nazi influence spread through German institutions. Colleagues who had once celebrated his achievements now distanced themselves, fearing association with someone marked as an enemy of the emerging regime. The intellectual freedom that had made Berlin attractive to Einstein was rapidly disappearing as universities came under pressure to conform to Nazi ideology and purge Jewish faculty members. The situation deteriorated dramatically after Adolf Hitler's appointment as Chancellor in January 1933. Within weeks, the Nazi government began implementing policies designed to exclude Jews from a German academic and cultural life. Einstein realized that his days in Germany were numbered, that the country where he had achieved his greatest scientific triumphs was becoming uninhabitable for someone of his background and convictions. Einstein was traveling in the United States when Hitler came to power, delivering lectures at Princeton University and other American institutions. As reports reached him of Nazi actions against Jewish intellectuals, Einstein made the painful decision never to return to Germany. He renounced his position at the Prussian Academy and began searching for a permanent refuge where he could continue his scientific work without political interference. The transformation from celebrated German scientist to stateless refugee was both sudden and complete. Einstein's books were burned in Nazi bonfires alongside works by other Jewish and liberal authors. His property was confiscated, his citizenship revoked, and a bounty placed on his head. The physicist who had once been Germany's most famous intellectual export was now declared an enemy of the state, his theories denounced as threats to national security and racial purity. American academic institutions competed for the opportunity to offer Einstein sanctuary. Princeton University's newly established Institute for Advanced Study emerged as the most attractive option, providing Einstein with ideal conditions for continuing his research while ensuring his physical safety. The institute promised complete intellectual freedom, adequate resources, and protection from the political turmoil convulsing Europe. Einstein's arrival in Princeton in October 1933 marked the beginning of a new chapter in his life, though one tinged with sadness for what he had lost. At age 54, he was starting over in a foreign country, separated from colleagues and friends, forced to rebuild his life around new routines and relationships. The German language that had shaped his thinking would gradually give way to English, though he would never entirely lose his accent or his attachment to European intellectual traditions. The Institute for Advanced Study represented a unique experiment in academic organization, bringing together leading scholars from various fields without teaching obligations or administrative responsibilities. Einstein found himself among distinguished colleagues including mathematicians Hermann Weyl and John von Neumann, creating an environment of pure research that resembled the idealized academic community he had always imagined. Yet Einstein's scientific work during his Princeton years was marked by increasing isolation from mainstream physics development. While younger researchers were making rapid advances in quantum mechanics, nuclear physics, and solid-state theory, Einstein remained focused on his quest for a unified field theory. He spent countless hours manipulating complex mathematical equations, searching for geometric relationships that would unite gravity with electromagnetic phenomena. This work was extraordinarily difficult and ultimately unsuccessful. Einstein's approach assumed that quantum mechanics was incomplete, that the probabilistic nature of atomic phenomena reflected human ignorance rather than fundamental uncertainty in physical processes. He famously declared that God does not play dice with the universe, expressing his conviction that underlying deterministic laws governed all natural phenomena. Einstein's opposition to quantum mechanics put him in direct conflict with most leading physicists of his generation. Niels Bohr, Werner Heisenberg, and other architects of quantum theory argued that uncertainty was built into the fabric of reality itself, that the act of measurement fundamentally disturbed atomic systems in ways that made precise prediction impossible. Their interpretation challenged Einstein's deepest philosophical convictions about the rational structure of the universe. The debates between Einstein and quantum mechanics advocates became legendary within the physics community. Einstein proposed thought experiments designed to reveal contradictions in quantum theory, while Bohr and his colleagues responded with increasingly sophisticated arguments defending the completeness of quantum mechanics. These discussions illuminated fundamental questions about the nature of physical reality and the limits of human knowledge. Einstein's most famous critique of quantum mechanics involved what would later be called the EPR paradox, named after Einstein and his collaborators Boris Podolsky and Nathan Rosen. They argued that quantum mechanics led to absurd conclusions about the instantaneous connection between distant particles, violating the principle that nothing could travel faster than light. Einstein dismissed such connections as spooky action at a distance, believing they revealed flaws in quantum theory rather than genuine features of nature. The scientific community gradually sided with quantum mechanics as experimental evidence accumulated supporting its predictions. Einstein found himself increasingly isolated, respected for his past achievements, but viewed as out of touch with modern physics development. His continued search for a unified field theory was seen by many colleagues as a quixotic quest, a brilliant mind pursuing an impossible goal through outdated methods. Despite his scientific isolation, Einstein's moral authority continued to grow throughout the 1930s and 1940s. His early opposition to fascism and his status as a refugee from Nazi persecution made him a powerful voice for human rights and democratic values. He spoke out against racism, militarism, and totalitarianism, using his celebrity to draw attention to causes he considered essential for human survival. Einstein's political activities during this period reflected his deep conviction that intellectuals had moral obligations beyond their professional responsibilities. He supported civil rights organizations fighting racial discrimination in America, recognizing parallels between anti-Semitism in Europe and racism in the United States. His advocacy for African American equality sometimes put him at odds with Princeton's conservative social environment. The outbreak of World War II in 1939 forced Einstein to reconsider his lifelong pacifist convictions. While he continued to oppose war in general, he recognized that Nazi Germany represented a threat to civilization itself that could only be stopped through military force. His famous letter to President Franklin Roosevelt, warning about the possibility of German atomic weapons research, helped initiate the Manhattan Project. Though Einstein himself was excluded from classified work due to security concerns, Einstein's role in the development of nuclear weapons remained indirect and largely symbolic. His equation, E=mc², provided the theoretical foundation for understanding nuclear energy, but he contributed no specific technical knowledge to weapons design. Government officials considered him a security risk due to his political views and international connections, keeping him isolated from the actual scientific work that led to the atomic bomb. The bombing of Hiroshima and Nagasaki in August 1945 filled Einstein with horror and regret. While he had supported Allied victory over fascism, he was appalled by the destructive power of nuclear weapons and their implications for human survival. He spent his remaining years advocating for international control of atomic energy and warning about the dangers of nuclear war. Einstein's post-war political activities focused increasingly on preventing nuclear conflict and promoting world governments. He argued that national sovereignty was incompatible with weapons capable of destroying civilization, that humanity needed supranational institutions to control technology that transcended national boundaries. His proposals for world federation reflected both his internationalist convictions and his understanding of nuclear weapons' transformative impact on international relations. The emergence of the Cold War between the United States and Soviet Union dismayed Einstein, who saw ideological conflict replacing the rational cooperation he believed essential for human progress. He criticized both American capitalism and Soviet communism, arguing that each system contained elements that threatened individual freedom and social justice. His independent political stance made him suspect to authorities on both sides of the developing confrontation. Einstein's final years were marked by continued scientific work on unified field theory, though he made little progress toward his goal of geometric unification of fundamental forces. He remained convinced that quantum mechanics was incomplete, that future research would reveal the deterministic laws he believed must underlie apparent randomness in atomic phenomena. His faith in rational understanding sustained him through decades of mathematical frustration and professional isolation. The man who had revolutionized physics through bold theoretical insights found himself defending increasingly unpopular positions about the fundamental nature of reality. Yet Einstein never wavered in his conviction that the universe possessed an underlying logical structure accessible to human reason. His persistence in pursuing unfashionable research directions reflected both intellectual courage and perhaps a touch of the stubbornness that had characterized his opposition to authority since childhood. Einstein's personal life during his Princeton years was quieter and more settled than his earlier decades of constant travel and public attention. His marriage to Elsa provided stability and companionship, though their relationship lacked the intellectual intensity of his collaboration with Mileva during his breakthrough years. Elsa's death in 1936 left Einstein increasingly dependent on his secretary Helen Dukas and his stepdaughter Margot for practical support and emotional connection. His relationship with his sons remained complicated by distance and the lingering effects of his divorce from Mileva. Hans Albert established a successful career as an engineer in California, maintaining cordial but infrequent contact with his father. Eduard's mental health problems worsened over the years, requiring institutional care that Einstein could observe only from afar due to his inability to return to Europe. Einstein's daily routine in Princeton became increasingly rigid and predictable. He would walk to the institute each morning, spend hours working on mathematical calculations, and return home for simple meals and evening reading. His appearance grew even more disheveled with age, his wild hair becoming an iconic symbol of scientific genius, divorced from conventional concerns about social presentation. Despite his advancing age and growing physical frailty, Einstein continued working on unified field theory until the very end of his life. His desk remained covered with pages of mathematical calculations, equations representing his final attempts to unlock the geometric secrets he believed governed all natural phenomena. The quest that had consumed his later years remained incomplete, a testament to both his intellectual ambition and the ultimate limits of individual scientific achievement. As Einstein entered his 70s, he had become something more than a scientist. He was a global symbol of intellectual courage, moral integrity, and the power of human reason to comprehend the deepest mysteries of existence. His theories had transformed our understanding of space, time, matter, and energy. His political advocacy had helped shape international responses to fascism, nuclear weapons, and the Cold War. His personal journey from patent clerk to global icon had demonstrated the possibility of individual genius transcending social barriers and conventional limitations. Yet Einstein remained haunted by the incompleteness of his scientific work and the persistence of human irrationality in political affairs. The man who had revealed the mathematical harmony underlying physical reality found himself unable to resolve the apparent contradictions of quantum mechanics or to prevent the nuclear arms race that threatened human survival. His final years were marked by a mixture of scientific frustration and moral urgency as he struggled to complete his theoretical work while warning humanity about the dangers it had created through technological progress divorced from ethical wisdom. The spring morning of April 18, 1955, dawned quietly in Princeton, New Jersey. Einstein woke in his modest home at 112 Mercer Street, the same simple dwelling that had sheltered him for over 2 decades since his arrival as a refugee from Nazi Germany. At 76 years old, his body was failing in ways his mind refused to accept. The abdominal pain that had troubled him for days was growing worse, but Einstein characteristically dismissed it as a minor inconvenience that would not interfere with his work. He dressed in his usual rumpled clothes, the uniform of deliberate indifference to social convention that had become as much a part of his identity as his wild white hair. His housekeeper, Helen Dukas, noticed that he moved more slowly than usual, but Einstein waved away her concerns with characteristic stubbornness. There were equations waiting on his desk at the institute, calculations that might finally unlock the geometric secrets he had been pursuing for 3 decades. The unified field theory remained tantalizingly out of reach, like a mathematical mirage that receded whenever he thought he was approaching it. Einstein had filled countless notebooks with tensor calculations and geometric manipulations, searching for the elegant relationships that would unite gravity with electromagnetism in a single theoretical framework. Each promising lead had eventually dissolved into contradiction or mathematical dead ends, but Einstein's faith in the rational structure of the universe never wavered. His colleagues at the Institute for Advanced Study had long since given up trying to dissuade him from this quest. They respected Einstein too much to openly criticize his work, but many believed he was pursuing an impossible dream through obsolete methods. The physics community had moved on to quantum field theory and particle physics, exploring realms of reality that seemed to contradict Einstein's deepest philosophical convictions about determinism and local causality. Einstein understood their skepticism, but remained convinced that time would vindicate his approach. He had been right about relativity when the entire scientific establishment was wrong. He had predicted the existence of photons decades before experimental confirmation. His intuition about the fundamental structure of reality had proved reliable before, and he saw no reason to abandon it now, simply because the mathematics was proving more difficult than anticipated. The morning routine at the institute proceeded as it had for years. Einstein would arrive at his office in Fuld Hall, greet his assistant Brurier Kaufmann with a gentle nod, and immediately immerse himself in the sea of equations that covered his blackboard and desk. The calculations required extraordinary concentration, manipulating complex mathematical objects that existed only in his imagination, but might correspond to the deepest structures of physical reality. Kaufmann had learned to work quietly around Einstein's intense focus, understanding that interruptions could break delicate chains of reasoning that might take hours to reconstruct. She watched him struggle with particularly difficult computations, his brow furrowed in concentration as he searched for mathematical patterns that would reveal new insights about the geometric nature of fundamental forces. The work was becoming increasingly difficult for Einstein's aging mind and body. The stamina that had once allowed him to work 18-hour days was diminishing, and the complex calculations required more effort than they had in previous years. But Einstein refused to acknowledge these limitations, driving himself with the same relentless determination that had characterized his approach to physics since his student days. During lunch breaks, Einstein would sometimes discuss his work with colleagues who visited his office. Abraham Pais, a young physicist who had become one of Einstein's few confidants about technical matters, would listen patiently as Einstein explained his latest ideas about unified field theory. Pais understood the mathematical sophistication of Einstein's approach while remaining skeptical about its ultimate prospects for success. These conversations revealed both Einstein's continued brilliance and his growing isolation from mainstream physics. He could still manipulate complex mathematical concepts with remarkable facility, but his physical intuition seemed disconnected from the experimental discoveries that were revolutionizing atomic and nuclear physics. The man who had once transformed physics by questioning its most basic assumptions now seemed trapped by his own philosophical commitments. Einstein's political activities during these final years reflected the same combination of moral clarity and practical ineffectiveness that characterized his scientific work. He continued to speak out against nuclear weapons and the Cold War arms race, warning that humanity was creating the instruments of its own destruction. His letters to world leaders urged international cooperation and the establishment of supranational institutions that could control nuclear technology. But Einstein's political influence was waning along with his scientific relevance. The governments he addressed were more interested in military advantage than moral arguments, and Einstein's reputation as a naive idealist, diminished the impact of his warnings about nuclear dangers. The man who had helped initiate the atomic age found himself powerless to control the forces he had helped unleash. The irony was not lost on Einstein that his most famous equation, E equals mc squared, had become associated primarily with nuclear weapons rather than the pure understanding of energy and matter he had originally sought. The mathematical relationship that revealed the fundamental equivalence of mass and energy had been transformed into a tool for unprecedented destruction, demonstrating how scientific knowledge could be divorced from the moral wisdom necessary for its responsible application. Einstein's personal relationships during these final years provided both comfort and frustration. His stepdaughter Margot cared for him with devoted attention, but she could not share the intellectual companionship that had once sustained him through difficult periods. Helen Dukas managed his correspondence and protected him from unwanted intrusions, but Einstein increasingly felt isolated from the community of scientists who had once eagerly sought his insights. His correspondence with old friends revealed a man grappling with the limitations of age while maintaining his essential curiosity about the nature of reality. Letters to Max Born, his longtime friend and occasional scientific adversary, continued their decades-long debate about quantum mechanics. Einstein remained convinced that the probabilistic interpretation of atomic phenomena was incomplete, that future discoveries would reveal the deterministic laws he believed must govern all natural processes. The letters also revealed Einstein's growing preoccupation with mortality and the meaning of his life's work. He wondered whether his scientific contributions would survive the test of time, whether his unified field theory would eventually be completed by future researchers, or whether his opposition to quantum mechanics would be vindicated by new experimental discoveries. These questions haunted him as he contemplated the approaching end of his remarkable intellectual journey. On April 17, 1955, the abdominal pain that had been troubling Einstein for several days suddenly intensified. He collapsed at home and was rushed to Princeton Hospital, where doctors diagnosed a ruptured abdominal aortic aneurysm. The condition was serious but not immediately life-threatening with proper medical care. Doctors recommended surgery to repair the damaged blood vessel, but Einstein characteristically refused the intervention. His decision reflected a lifetime of thinking about death as a natural process that should not be artificially prolonged. Einstein had no fear of dying, viewing death as simply another transformation in the endless dance of matter and energy that constituted the universe. He had spent decades contemplating the mathematical relationships that governed physical reality, and he saw no reason to cling desperately to biological existence when his body was clearly failing. Albert Einstein passed away quietly in his hospital bed in the early morning hours of April 18, 1955, his final equations still scattered across his desk at the Institute, his quest for a unified theory forever incomplete. The boy who questioned a compass needle had become the man who revealed the universe's deepest secrets, transforming our understanding of reality itself. From patent clerk to global icon, from revolutionary thinker to moral conscience of humanity, Einstein's journey reminds us that curiosity, courage, and relentless questioning can reshape the world in ways we never imagined.